Welcome back to another tutoring. In this video we're going to be looking at efficiency and energy sources. Okay, so as you can see we're on the third video of three, so 3 of 3 in the first topic of energy. As you can see, the diagram at the top splits into here. In our next session, if you're following along with the workbooks and test papers, I would recommend that you do the test. If you're just watching the videos, then the next one is the first electricity video. Let's crack on. So, efficiency. Efficiency is a way of measuring the ratio of input energy to wasted energy. Efficiency gives you a good understanding of how much energy is being wasted for a particular appliance. This means you can choose better appliances with a greater efficiency. Efficiency is given as a decimal or as a percentage. So, the efficiency of an appliance is how much of that energy is used in useful ways, where you get useful energy transfers. So, for example, in a speaker system, you would want more energy to be converted into sound and less energy to be converted into heat. So a speaker system which converts more of the electrical energy which is going into it into sound energy would be more efficient. So if you were buying a kettle, for example, it would be much better to purchase a kettle with high efficiency, because then a higher percentage of the electrical energy is being transferred into heat and not other forms like sound energy. Remember, in every system there's always some lost energy, which we call wasted energy, and that means nothing is 100% efficient. No energy transfer is 100% efficient. There will always be lost energy to heat, sound, or other unwanted stores. As we see in the last video, Sankey diagrams can be used to help work out the efficiency, but often efficiency will just be given as a percentage or even as a decimal. To work out the efficiency, you use this formula, and again, you do need to learn this formula. So the efficiency is equal to the useful output energy divided by the total input energy. So if I have, let's go back to the kettle example, I have so much energy going into the kettle, which would be electrical energy, well that would be the total input energy on the bottom of the fraction. The useful output energy, well that would be the amount of energy which is being converted into thermal energy, because that's what happens in a kettle. You want heat, you want to heat up the water. So that's one of the equations which you need to learn. So here's a little working example. An oil heater is 95% efficient. Work out the amount of heat energy produced from 175 joules of chemical energy from oil. Okay, so the first thing we're going to do is write out our equation, and our equation is efficiency is equal to useful power output over total power input. Or energy input and energy output. You can use both energy and power. So 0.95, well that's our efficiency because it's given to her in the question. 95% is just 0.95 in a decimal. So 0.95 is equal to useful output divided by 175. So the useful output, if we rearrange that formula a little bit and we multiply, we get 175 times 0.95. So our useful output energy is 166.25 joules. There are ways to make energy transfers more efficient. In the exam, you may be given a question which asks you to describe how you can make something more efficient. In these cases, you just have to use your initiative. One example is heating water in a pan. A way to make the process more efficient is to buy a bigger based pan, so more of the heat from the element passes into the pan. Use a lid for the pan to reduce wasted heat, and use a more insulating material for the sides of the pan. So if you have a pan and you have the heating element on the bottom, you want less of that heat to escape through the sides of the pan, so you can use an insulating material around the sides. If you have a bigger based pan, then more of that heat which is being produced in the element will go into the pan and not escape around the sides. And obviously if you use a lid, you're keeping more of that heat energy in and you're not letting the heat dissipate and move into the surroundings. In motors or factories with moving parts, electrical energy is often transferred into kinetic energy. In these situations, friction acts on moving parts in contact with each other. This slows it down and makes the transfer of the electrical energy into heat energy. And obviously, when you've got moving parts, you don't want heat energy, you want kinetic energy. To tackle this, you can lubricate moving parts by adding oils and other liquids. These mean the surface is more slippery and less rough, so friction is reduced, and so is unwanted energy transfer from electrical to thermal. So if you lubricate moving parts, what you're doing is you are making less friction. The force of friction reduces. And if you have less friction, you get less heat being generated. And if the electrical energy is being converted into kinetic energy rather than heat energy, then you're making that machine or that part more efficient, and that's what you want. So by lubricating moving parts, you get more efficient machinery. For industrial processes, it is important that conditions are kept at a certain temperature. This means heating is necessary, but after time, the thermal energy will move away from the source of heat and be wasted as the heat was not intended to go there. To counteract this, thermal insulation can be installed. This means less heat moves away from where you want it to go. So, if you're in a factory and you want a specific place to be a certain temperature, let's say you're causing some sort of chemical reaction, for example, if you want the heat to be concentrated in one place, what you can do is you can insulate around that place so less of that heat escapes and goes elsewhere. So by insulating the area where you want the heat to be, what you're doing is you're stopping the wasted energy, because less of the energy which you're producing is dissipating and travelling elsewhere. So that makes it more efficient, doesn't it? Because you more of the energy which is going into heating that area will be contained there rather than travelling away. Okay, so if you're following along in your revision workbook, pause the video and do task number 8. And for this task, there are 2 pages, just because I'm very kind to you. Okay, so convection and infrared radiation is what we are doing next. Conduction and convection are ways heat moves through substances. For the topic of energy, you need to know about convection. Convection is the process by where heat moves through liquids and gases. Here, particles vibrate and collide with other particles. This space is less dense than spaces which are cooler. This means that this air, the heated air / liquid, rises and forms cells of convection. Heat moves through rooms. So, convection. Convection is where you have, let's say you've got a group of particles, you've got air particles in a room, okay? When you heat some of those particles up, what happens is they become less dense, and they become less dense because they're getting more excited. As you heat particles, they gain kinetic energy, they gain speed, and what you get is, because they're travelling so quickly and there's more spacing between them, it means there's less particles in that same volume, so you're getting a less dense batch of air. So the heated air is less dense, and what you find is, you find that less dense gases and liquids rise to the top, and the more dense, particles, the more dense batches of air go to the bottom. So what you actually find is, you find that in rooms which have heaters and things like that, you get convection currents where there's particles which have been heated up and they travel up, and then when they get to the top of the room, they travel along and then back down again, and as they cool down, they travel back towards the radiator. So you actually get currents of convection because of the heaters in your room. So convection is where gas particles move and heat moves through gases and liquids in that way. Infrared radiation is heat energy in the form of waves. This moves through the air and other mediums. So later on we'll look at infrared radiation as part of the electromagnetic spectrum, but that's way down the line. That's when we'll look at waves. But infrared radiation is essentially a third way which heat can move. You don't actually need a medium for that, so you don't need air particles, you don't need a solid like for conduction. This can actually happen in a vacuum, so this can happen in without particles, and infrared radiation transfers energy in the form of electromagnetic waves rather than particles vibrating. Conduction is where heat spreads through solids. In solids, particles vibrate, and it is this that we feel as heat. So when we touch something which is hot, the particles are vibrating a lot, and that's actually what we feel as heat. The particles vibrate and cause others to vibrate, so the heat passes along through the solid as a type of chain reaction. So if you imagine a pan, and you imagine a handle on the pan. If the pan is hot, the end of that handle nearest the pan will also be quite hot. And let's say that's metal. What you will get is those particles will be vibrating a lot because they're hot. And those particles vibrating backwards and forwards, they will hit the other particles which are less warm, less hot, and then they will start bouncing backwards and forwards as well. And this is a sort of chain reaction, and it'll move up the pan handle. And that's how conduction works in solids. These particles are vibrating, and these cause chain reactions, so the heat spreads through the medium. The higher the thermal conductivity of a material, the higher the rate of energy transfer by conduction across the material. So if you have a material with a high thermal conductivity, then the energy transfer through heat will be quick. It'll travel through that material quickly. Buildings can be made more energy efficient, so buildings need to be heated, and the energy is normally sourced from chemical energy in a gas or electrical energy made in power stations, both of which are damaging to the environment, and they both cost money as well. Gas and electricity is expensive, and gas being burnt releases carbon dioxide into the atmosphere, and electricity being generated often comes from non-renewable sources, causing air and water pollution. So essentially what we're saying is, all of these ways to heat your home, gas and electricity, they both cost money, which is, well, not a good thing, and they both are relatively bad for the environment. So buildings should be made as energy efficient as they can be, so we're not burning through fossil fuels and all that sort of thing to make electricity or to heat our homes with gas. The walls of a building affect the rate of cooling inside the household. If the building has thicker walls, then it takes much longer for the heat to get through, as more conduction is required, which is a time-consuming process. If the building's walls have a lower thermal conductivity, then it's harder for heat to escape, as conduction occurs at a slower rate. So, if you have more insulative walls, and insulation has obviously low conductivity, then the building will retain the heat inside for longer. So it requires less energy to be converted into heat, and that makes the building more efficient. So how can buildings become more efficient? Well, buildings can be made more efficient in a variety of ways. Insulators, remember, they do conduct, but it's just very slow. The first way you can insulate your home is insulation, and insulation in the roof can stop heat escaping so quickly. This is because, as we know already, heat rises and the physical barrier will keep heat inside the household. So if you have insulation in your roof, it will stop the thermal energy rising and going up and leaving the household. Cavity wall insulation can also help keep heat in. With thin walls or walls which are made from a conductive material, let's say metal, cavity wall insulation helps hugely because there is another physical barrier to heat getting through. So if you've got, as this picture here shows, if you've got two different types of wall like this, you can put cavity wall insulation in between. That's on its side, that picture, obviously. This would be cavity wall insulation in the inside. It's often like a sort of foamy material, and that's a good insulator. It's a very low conductor of heat. So what happens is the heat which is inside your house takes much longer to move through that cavity wall insulation, and you retain the heat for longer, and that makes your house more efficient. Number 2, draught excluders. Draught excluders do exactly what the name suggests. A draught is caused by a difference in heat, and when heat comes into contact with cold air, convection occurs. So if you have a door and the inside of your house is warm and the outside is cold, well, obviously that heat wants to escape because heat travels to places which are cooler. So if you put a physical barrier in the way, you will stop that warmth from leaving. You will stop that heat energy escaping your house. So a physical barrier can stop this from happening. Draught excluders can be found under doors to keep heat in, and from escaping under and above doors, and in windows. Number 3, double or triple glazed windows. Windows with extra panes of glass keep heat inside. This is because there is a double or triple the amount of material that conduction has to work on to get through, keeping heat in for longer. So if you have 3 layers of glass in a window, what you get is you have a part where there needs to be conduction to get through the glass, and if you have a gap, you then have to go through convection, then another pane of glass where you have to go through conduction, then another bit of air where you need to go through convection, and then a third layer of glass where you've got to go through conduction again. So if you have 3 panes of glass, you have a very large amount of insulation, effectively keeping the heat in your house and stopping it from leaving. If you're following along in your revision workbook, pause the video now and complete task number 9. Alright, so our final part of the energy topic is about energy sources, where energy comes from. Energy can't be created, as we've went through many times, but in order to be used in useful ways, we need to get it from somewhere. We need to get it from sources. Some sources are better than others, as they may have a higher power output or be better for the environment. In our society, we use energy for 3 different things: electricity generation, transport, and heating. Well, those are the 3 that you need to know about anyway. So, what is renewable? What does that word mean? Renewable energy sources are sources which are more sustainable. Renewable energy sources do not use up anything like materials which will eventually run out, but instead take advantage of a process like wind power. Non-renewable resources take up resources and will eventually run out. So we're going to look at several sources of energy, and the first one which we're looking at is fossil fuels, and that sums up oil, coal and natural gas. Fossil fuels store energy in their chemical store. Fuels are non-renewable, so fossil fuels will run out one day. They're used for transport, heating and electricity generation. So if you take fossil fuels and burn them in a power station, you can use that heat to turn turbines and generate electricity. You can burn coal in fireplaces to keep you warm, or you can put fuel in a car and that will provide you with transport. They do have a high power output, so fossil fuels are good if you want a high power output. From a small amount of fuel, you get a lot of energy being released in a short time. But they release carbon dioxide, which is harmful for the environment and causes global warming. So fossil fuels are bad for the environment. Nuclear power. Nuclear fuels store energy in their nuclear store. So that's the store inside of atoms. They are non-renewable, but as they will last so long, we actually put nuclear into its own category, recyclable. So nuclear energy will last us for absolutely ages. Because of this, it is technically a non-renewable, because eventually we will run out of nuclear fuel, but that is a very long way away from happening. Nuclear fuels are used for electricity generation only. At the minute, you don't get nuclear-fueled transport or nuclear-fueled heat. You only get nuclear-fueled electricity generation. There is a very high power output, so nuclear power is very good for us. Very small amount of fuel, you get a lot of energy in quite a short time. There is radioactive waste which needs to be discarded safely. So this is a big problem with nuclear energy. Nuclear power stations release no carbon dioxide, which makes them quite clean for the environment, but they do have radioactive waste which needs to be discarded of safely, and that's a big task. Often you need to bury it quite far underground. Number 3 is biofuels. So biofuels store energy in their chemical store. Biofuels are renewable as they can be regrown. They're used for transport, heating and electricity generation. So you can burn biofuels in power stations, you can heat your house with biofuels, and there are quite a few forms of transport now which use biofuel. There's some biofuel buses, you can even get biofuel-fueled farm equipment as well. They have a medium power output, so not quite as bad as some energy sources, but still not quite as good as things like fossil fuels and nuclear energy. Biofuels are known to be carbon neutral, although large areas of rainforest are being chopped in order to grow biofuels. Often biofuels are grown as palm oil, and palm oil is, well, they come from palm trees, and palm trees are being planted in the places where forests used to be, in places like the Amazon. Next is wind. So wind energy is kinetic energy, or wind energy stores its energy in its kinetic store. It's renewable, one of the most renewable sources of energy. It is used for electricity generation only. But wind power has a very low power output, so for quite a lot of windmills you get a relatively low amount of power. The environmental impacts are that it takes up lots of land, which could be used for farming or something else, and people have the opinion that windmills are ugly. So there's people called NIMBYs, not in my backyard. People who say, oh, windmills are very good, but I don't want them near me. If the weather is not windy, the power output is very low. So wind is unreliable, because if it's a day where there isn't a lot of wind, then you can't guarantee you're going to get a lot of energy being produced. So wind is good, but unreliable. Number 5 is hydro. So hydroelectricity is gravitational potential energy. It's renewable and it's used for the generation of electricity only. So hydroelectric power works by damming a river and allowing that water to flow through. But when the water flows through, it turns the turbines which generate electricity. So hydroelectricity has a medium power output. Unfortunately for hydroelectricity, dams need to be built across rivers, disrupting local habits and habitats. It means fish struggle to swim up and down the river, and that areas need to be flooded. So often when you dam a river, you get a big area behind it which is flooded. And in some countries, people depend on the river for washing and for even maybe drinking, that sort of thing, And by damming a river, you reduce the amount of water which goes through, which can lead to problems, socio-economic problems, and it can lead to fish and things which travel up and down the river having a lot of disruption. So next is geothermal. So geothermal energy comes from thermal energy. It's renewable. The ground will always produce heat due to radioactive decay in the centre of Earth. Used for electricity generation and heating, geothermal energy has a medium power output and there is a very low environmental impact. So geothermal energy works by pumping water very, very deep down into Earth, where it's quite warm. So the further you go down, the warmer you get, essentially. So what you do is you pump the water down very far into Earth, it heats that water up, and then the water comes back up to the surface and it's warm. 7 is tides. So energy is stored as kinetic energy in tides, essentially. Tidal electricity is renewable, as tides will never get used up. Tidal power is used for electricity generation, and the power output is potentially very high, but it is hard to install. Tidal barrages can block sewage which needs to go out to sea in developing countries and is bad for marine life, a little bit like the hydroelectric dams. So tidal electricity works by putting a big barrage along sort of a seafront or a river which is tidal, and what you do is you allow that water to rise with the tides, and then you shut a big door and it traps the water behind. Then you let the water go down with the tides, you open up the doors and you let the water go through, and that turns the turbines which generates electricity. Number 8 is sun/solar. So solar energy comes from light from the sun. It's renewable, at least until the sun dies out, but we don't need to worry about that because we won't be around in the first place when the sun dies. So there will be no need for electricity when there's no people on the planet when the sun dies. But this is used for electricity generation and heating. The sun's power is dependent on time of day and the weather. So if you have a cloudy day, you do get a little bit less power from solar power. And again, it's very dependent on the time of day. Solar energy is, around during the day because that's when the sun's out. There is very little environmental impact with using solar panels. So despite the fact that they take up a lot of room, which again could be used for other things, the environmental impact is relatively low compared to other types of energy production. Number 9 is water waves. So waves have energy in their kinetic store because the water is moving. Waves are a source of renewable energy, they will never be used up. So the wind causes waves and the waves travel towards the shore and we can use that energy to generate electricity. It's only used for electricity generation and there's a low power output from this source. However, with wave energy, the environmental impact is tiny. So you get a low environmental impact with water wave energy. In the exam, you may be asked to compare different types of energy sources. It's important that you look at what the issue is in the question. Do they need lots of power, or is it that they are more concerned about the environment? If you ask yourself this, then you will do better in the exams for questions of this sort of type. So often, you might get sort of longer worded questions, maybe a 4-mark question, maybe even a 6-mark question, asking you to compare different types of energy source. Certain types of electricity are more reliable than others. Nuclear and fossil fuels are more reliable as you can increase the supply as demand increases. With solar and wind, you're relying on the weather, so you may end up with much less of a supply than what you actually need. So it's all about looking at what the question is asking you about and prioritising what you think the situation needs. So if they need a lot of power, you might want to go for the fossil fuels and the nuclear energy, but if it is the environment that the question is more concerned about, then obviously you would favour things like solar, things like wind, or maybe even waves or tidal. Complete task 10 in your energy workbook if you are following along. And after you've done that, we have finished the first topic. Well done. That's the first topic of the Physics GCSE, energy. And if you want to test your knowledge, you can head over to the website, take the test. Good luck. Thank you very much for watching. Workbooks and test papers which integrate with these videos and online courses are available at our website, backrowtutoring.com.